You are here because you have shown interest in OFDM and its technology. In this presentation, we're going to rethink the mathematical basis of OFDM. We will offer evidence that the OFDM data rates can be improved by a factor of at least 2 with little change in transmitter hardware. OFDM is arguably the most significant technology of the 21st century because it is the enabler of all high-speed digital communications. And because of this, OFDM may be the most heavily researched technology on a global basis over the last 50 years. The key to our new approach will be replacing the FFT at the receiver to achieve faster symbol demodulation without sacrificing the graceful degradation of the current OFDM implementations. We will also rethink the cyclical prefix, the channel equalization methods, and the receiver frequency synchronization. We do not propose tweaks of OFDM mechanizations, but a new way of looking at sending data across a channel. We're not communication specialists, so our terminology and understanding of the basic technologies may be suspect. Therefore, we have interest in partnering with a communication specialist or firm. Please contact us by email or telephone if you have further interest after hearing what we have to say here. Similarly, contact us with any errors in our presentation and any other analysis and simulation that you would like to see. We will cover a lot of ground in this material, so let's do a quick summary. We'll first go over the traditional OFDM mechanizations and concepts. Our strategy will be to motivate the new approach by showing that it resolves some constraints that are imposed by the traditional approach. We will introduce a new differential equation representation of an oscillating wave that will allow more flexibility than the more traditional exponential notation representation that is used by the FFT algorithm. Next, we will introduce the QAM-modulated single carrier as a stepping stone to the multi-carrier model. And we will show how the new approach works well with the widely accepted QAM modulation scheme. Then we will extend the single carrier system to a 2-carrier system with both carriers closely spaced and modulated with QAM. We will see that orthogonality of the 2 waveforms is not a factor in subcarrier separation. Finally, we will increase the subcarriers from 1 carrier to 64 subcarriers to show the straightforward extension to a practical 802.11 waveform. This final section will also introduce the radio implementations where we increase the data rate by a factor of 2. Before we discuss the new algorithm, we will introduce a few definitions. We show a general definition of a sine wave. The A and B coefficients of the cosine and sine terms can be transformed into the magnitude and phase of the sine wave, as shown. The subscript n suggests that there will be multiple sine waves, each with a different frequency and A and B values. For OFDM, the discrete change of A and B at a time, t sub k, is used rather than modulation of the carrier phase and amplitude. This method is called quadrature amplitude modulation, or QAM for short. The A and B values at discrete time, t sub k, are selected from a predefined grid pattern at the transmitter. We show an 8x8 grid pattern on the left and a 4x4 grid pattern on the right. These are designated as 64 QAM and 16 QAM, respectively. We will choose to fix the corners of the grid pattern at a plus or minus 1 for our developments. The receiver's job is to sample the received signal and then to decode the transmitted A and B values, which are then mapped into a bit stream, as we will show more shortly. The lower QAM values have A and B values that are spread further apart, so that the receiver will have an easier time in decoding the A and B values in the presence of noise. The pre-assigned grid pattern for the QAM is called the constellation. We will use MQAM as the more general definition of QAM, where the square root of the M defines the rectangular grid pattern. On the right side, we show the single carrier representation in the frequency domain. We note here that the QAM modulation can be used with a single carrier as well as with a multi-carrier waveform. We will show our new algorithm first using the single carrier and then extend to the multi-carrier. OFDM, of course, will use multiple subcarriers, and we show that on this slide. On the right side of the slide as multiple carriers spread across a bandwidth. 802.11, for example, has 64 subcarriers spread across a 20 megahertz bandwidth. Given this specification, the frequency separation for the subcarriers will be exactly 312.5 kilohertz. That is 20 megahertz divided by the 64 subcarriers. For the more recently released 802.11ax specification, the number of subcarriers has been increased to 256 with a frequency separation of 78.125 kilohertz in order to maintain the same 20 megahertz bandwidth. At this point, we see that each A and B pair or constellation grid point can represent a new piece of information. Also, each of the 64 subcarriers can be encoded with a unique A and B pair. Use of these multiple subcarriers and the QAM modulation approach provides OFDM with a significant degree of parallelism that is one key to the achievable high data rates from OFDM. The actual A and B pair selected from the transmitter constellation is referred to as a symbol. So the constellation is the available set of A and B values defined at the transmitter, whereas the symbol is the chosen A and B pair that points to the information that is to be transmitted. The waveform at the receiver is digitally sampled, and an algorithm is applied to the samples in order to decode or demodulate the information that is pointed to by the A and B pair. For the FFT algorithm, we must complete the sampling of the summed multi-carrier waveform at the receiver before we can begin to process these samples. The receiver sampling time for decoding the information is known as the symbol time. The receiver sampling rate and the number of samples is fixed due to the use of the FFT at the receiver, and we'll say more about this shortly. It is well known that the symbol time for the FFT demodulation algorithm is explicitly linked to the frequency separation of the spaced subcarriers. The symbol time delta t, in fact, is exactly equal to the inverse of the frequency separation as shown on this slide. And the digital sampling rate is 64 times the symbol time, or 20 megahertz. Furthermore, the FFT requires exactly 64 digital samples in order to perform the demodulation. Something curious that came to my attention is that we will say more, and we will say more about this later, that there are 64 digital samples taken at 20 megahertz for a waveform with 20 megahertz bandwidth. From our Nyquist theory, we would expect that we cannot resolve the A and B values from the sample data set. We should sample at twice the bandwidth. Isn't this correct? We'll say more about this later. The symbol transmission for the set of modulated subcarriers occurs in a repetitive manner. to form what's called a frame. An example of a frame is shown here for 802.11a. The frame is important to OFDM because there is a preamble to each frame where calibration information is sent across the channel to allow modeling of the channel's influence on the transmitted waveform. The calibration information includes pre-assigned A and B values that are values that are fixed for all mechanizations, and the A and B values will be known at the receiver. Errors in the received estimates of these known transmitted values are used to correct the A and B values that are contained in the data symbols. Also, this transmission of pre-known values enables calibration of the receiver's sampling clock, which may differ from the transmitter's sampling clock. The transmitter also sends a single symbol after the preamble to inform the receiver of the waveform properties. For example, the specific QAM constellation. Now we can show the standard representation for an OFDM mechanization for single symbol time, not the frame. Starting at the upper left, a bit sequence, that is S sub n, enters the transmitter. This bit sequence may be data or other preamble messages, but it is in fact a symbol. The transmitter's selected MQAM constellation can represent M unique values. 16 QAM can represent 4 unique bit patterns, and 64 QAM can represent 6 unique bit patterns. The general expression for the number of transmitted bits per symbol time is 2 to the bits raised to a power equals M. We will say more about this equation later because it becomes quite important. For example, 1024 can represent all unique values that can be formed from 10 bits. The S sub n sequence is broken into constant length subsets based upon the selected MQAM. These are then mapped into A and B pairs or symbols using the MQAM constellation layout. The array of A and B pairs, one for each subcarrier, form the input to an inverse Fourier transform, or IFFT. The IFFT transforms a set of frequencies into their time domain representation. The IFFT's real and imaginary outputs, both in time domain, are a discrete representation of a time history formed from summing the sine waves defined by the A and B pairs. The digital analog converter creates a continuous version of the discrete time history that is provided by the IFFT. So far, everything is done on sine waves that begin at DC and extend to the bandwidth extreme. For example, at 20 megahertz with the sine waves being equally spaced in frequency. So next, we must upconvert the real and imaginary time histories at baseband to the carrier frequency. For example, 2.4 gigahertz. This is done using an IQ mixer device that has the ability to transmit 2 separate time histories across the same bandwidth. The receiver is just the inverse of the transmitter. That is, all operations on the receiver are just the inverse of the transmitter. The receiver's IQ mixer does the down conversion back into the original baseband and the separation of the real and imaginary time histories using the 2 channels of the IQ mixer. The FFT, that is the forward FFT, then transitions the time history back into the frequency domain to recover the A and B values that can then be mapped into the sequential bit pattern, based upon, of course, the known constellation. We have also added the forward error correction. This is an important step that adds extra bits to the transmitter's sequential bits in a manner such that we can both detect bit pattern errors and we can correct certain bit patterns without requiring the transmitter to retransmit its pattern. The significance of this feature will be discussed further later in this presentation. Now we can show the expression for the OFDM data rate in some terms that we have already described. The FEC inserts extra bits that act as an overhead to improve robustness of the system. For example, a 5/6 FEC will insert a single added bit for every 5 bits, or a 20% reduction in data rate, but quite effective in recovering data if we have errors at the receiver. Next, the bits per symbol is linked to the selected MQAM at the transmitter and can range from 1 bit all the way up to 10 bits. Next, the subcarrier A and B is not fully populated with data. That is, this set 802.11, for example, has 64 subcarriers, but all of them do not actually carry data. Some subcarriers at the low and high ends of the bandwidth have 0 values for A and B in order to prevent interference or spillover into the neighboring 20 megahertz channels. Also, some subcarriers transmit pre-assigned or known values of A and B that can be used to adjust the channel calibration parameters. Recall the channel calibration was done as a part of the receipt of the preamble, but we can also do some within symbol calibration based upon these known pilot subcarriers. For 802.11 AC, only 48 of the 64 subcarriers carry data, which is in fact a 75% reduction in throughput. The symbol time in the denominator is explicitly related to the subcarrier separation and cannot be adjusted because of the FFT algorithm. And we're going to say a lot more about this later. Finally, the guard time is added to the symbol time in order to allow delayed portions of multipath signals to be received at the receiver. For 802.11, this guard time can be as much as 20% of the symbol time. That further reduces the data rate. And again, we'll say more about this later in the presentation. At this point, we have provided no detail on a new algorithm for demodulating OFDM subcarriers. The mathematic we will use to define the multi-carrier model will in fact define the demodulation algorithm. So let's talk about models for an oscillating wave. The first multi-carrier model at the top of this chart should be familiar. It's just from the Fourier series used to represent any arbitrary time series. This form of multi-carrier model is constrained by having its subcarrier frequencies both equally spaced in frequency, and it must include a DC component. The second math model uses the discrete Fourier transform, or DFT, and represents the subcarriers with an exponential complex representation. This allows use of the FFT for a fast numerical solution, but further constrains the model. This model has the equispaced frequency constraint and the DC constraint, and it adds a constraint on the digital sampling frequency. That is, the digital sample interval must equal to the inverse of the frequency separation. This use of the FFT for fast digital processing is what imparts the orthogonality constraint to the subcarriers, and not the ability to separate the closely spaced subcarriers, as we will show shortly. At the bottom, we show the new differential equation form for the oscillating wave. The differential equation model removes all of the constraints imposed by the other models. It allows arbitrary frequency layout for the subcarriers, including non-equally spaced frequencies. It allows for an arbitrary digital sampling pattern, including non-equally spaced samples. And it allows for a known DC offset that is applied to all subcarrier frequencies. The modulated A and B terms are represented in the solution exactly as before. The benefits of removing these constraints will be evident shortly. Because of its importance, let us restate this in a different way. The top equation on this chart is the most general expression for a summation of a set of oscillating waves. We can have an arbitrary frequency layout and an arbitrary sampling interval, and we can specify a frequency offset. We can easily show that this is a solution to the second order differential equation that is shown to the right. The frequency offset term, omega sub 0, in this model will allow the use of a direct RF sampled mechanization with no mixer for down conversion. This will be discussed further as we get into the new algorithm. The middle equation is a Fourier series representation that begins at a zero frequency, or DC, and must have evenly spaced frequencies. The closed form solution for A and B is what motivates the equally spaced frequencies. But the digital sample rate can be selected arbitrarily. It only requires a rate much faster than the highest frequency or the bandwidth of our signal. The third model leads to the exponential complex form used for the FFT. The FFT math form is a direct result of applying the sample rate constraint to the Fourier series and also applying the Euler equation for the exponential form. The digital sampling interval must be related to the frequency separation as shown in order for the FFT to achieve the n log n processing improvement. We will present the new algorithm in a few slides, but first we want to motivate our expression for the bit error rate, or BER. Operating at an acceptable BER goes hand in hand with the goal to achieve a high data rate. Let's step back to the QAM definition. This chart shows a 16 QAM constellation along with its mapping into a 4-bit pattern. For the 16 QAM, we know that we can transmit a unique 4 bits in a single AB pair from the constellation. Look at the bit pattern 1110 that's shown in red near the top of the page. We can see that the A has a value of 0.33 and the B has a value of 1.0. This provides us with an oscillating wave that you see there on the right. This is all predetermined at the transmitter, and the OFDM frame preamble communicates to the receiver the nature of the transmitted in-QAM constellation. We know that a larger distance between M-QAM grid cells, or a lower value of M, will lead to more robustness to noise at the expense of the data rate. A method is needed to quantify this relationship in order to be able to associate the A and B estimation accuracy to the bit error rate, or BER. The top expression on the right is a general expression for the M-QAM grid cell size given M. The 2 in the numerator is the magnitude of the sides of the grid between plus and minus 1. We must divide this by the square root of M subtracting 1, as can be seen from the grid example. This is a general expression for the M-QAM grid cell size for any value of M. The new algorithm will provide accurate estimates of the standard deviations for A and B. For acceptable BER, these estimate standard deviations must be small with respect to the MQAM grid cell size. We will choose 6 times sigma as the desired cell size, with the assumption that the joint Gaussian density for A and B will be circular. That is, the A and B estimate sigmas are equal and the estimates are uncorrelated. We can set the grid size to 6 sigma as shown, and we know the fixed relationship between the number of bits per symbol and M. Using these 3 expressions, we can compute the bits per symbol as a function of the estimate sigma. This is a general expression for the bits per symbol, requiring only that we know the accuracy of the A and B estimation. We can compute the probability that the A and B estimates are within the correct rectangular grid cell using the Gaussian error function, or ERF. We show the probability of a correct assignment of the A and B estimates, which is 0.9973 squared, assuming the A and B estimate accuracy is within 3 sigma. The probability of a single bit error is just 1 minus the probability that the A and B are in the correct cell. This is 0.00539 for this example. The assignment of the constellation's A and B grid pattern to a specific bit sequence uses what's called gray coding. Gray coding means that any receiver estimation error that assigns the A and B into an erroneous neighbor grid cell will result in only a single bit error. Let's look at some actual simulation results for the A and B demodulation. We will not be using our new algorithm here. We're just adding simulated Gaussian noise to randomly selected A and B values based upon the MQAM grid cell size. The 64 QAM pattern that we show here dictates the grid cell size to be 2/7 or 0.29. And our noise standard deviation for A and B is 1/3 of the grid cell size. We repeat our equation from the prior slide here to show our expected results from the simulation. For our theoretical computation of the probability of bit error, we expect 5.39 single bit errors per 1,000 trials. Any single bit errors would all be corrected by the FEC. 2 simulations were done with 100,000 and 1 million samples respectively. The BER results were 0.00408 and 0.00403. These are a bit low from our predicted values. That is, the simulation results were actually better than the expected. This can be explained by observing that some estimate AB pairs fall outside the grid cell, but were in fact correctly assigned. These are the ones on the edges, as you can see more clearly from the zoom of the lower right grid cell. We could account for these outliers in the probability math with a bit more work. A 1-bit error is correctable with the FEC overhead. We could arrive at a 2-bit error at the receiver if the A and B estimates jump all the way across a neighbor cell. This would require a 9 sigma error in A or B. A higher probability for 2-bit error comes from jumping diagonally to a neighbor cell. This is the probability of A and B both being outside of 3 sigma, also easily computed with some probability math. The best way to significantly increase the OFDM data rate is to reduce the symbol time. Reducing the symbol time for a fixed subcarrier structure means that the FFT algorithm must be replaced. As you may have guessed already, the proposed algorithm is the Kalman filter. Let's go over some of the reasons why this is a good choice. The Kalman filter works well with linear systems defined by differential equations and with measurements that are linear in the system states. The model for the Kalman filter dynamics and measurement will be described in detail on the next slide. The Kalman filter math model can include noises on both the dynamic states as well as the measurements, with zero mean Gaussian noises characterized by their standard deviations. The basic model assumptions for the Kalman filter are identical as for the FFT, with the exception that a broader range of numerical solutions is allowed. The Kalman filter is an optimal estimator in a maximum likelihood sense. That is, there can be no better estimator in either speed of convergence or accuracy. This is a valid statement so long as the models and noise assumptions are correct. Do not underestimate the power of this statement. The algorithm that we will propose cannot be improved upon so long as the underlying model is valid. The Kalman filter numerical processing is incremental, so that each new measurement is processed as it is taken. This is in contrast to the FFT, where all data must be in hand at the end of a symbol time. The Kalman filter naturally provides a covariance matrix as a product of the algorithm implementation. This covariance matrix is also accurate so long as the system models are linear and correct. Along the diagonals, the covariance contains all the sigmas for all the A and B estimates. The correlation coefficients between all the A's and B's are on the off diagonal of the covariance matrix. Finally, the Kalman filter residual process is the one step ahead predicted error, as you'll see on the next few slides. The statistics of this residual process are well predicted by the Kalman filter. Monitoring the residual process relative to its predicted statistics can be used for model identification. That is, we can detect an unmodeled occurrence, as in the case of an unexpected discontinuity presented by a multipath signal. This may be the most significant aspect of the Kalman filter. Once the stochastic model for the dynamic system and the noisy measurements are defined, the Kalman filter algorithm also becomes well defined and, in fact, is a bit anticlimactic. The dynamic system must be first placed into a state space format, as shown here. The two states are the signal and signal rate. A digital version that uses the transition matrix is shown to the right. We show the exact form of the 2x2 transition matrix for the single carrier. We will model a single carrier here, and then we'll extend this single carrier model to the multi-carrier later. The measurement model is shown here with its additive white Gaussian noise. The measurement matrix H reflects that the measurement is of the signal S and not the signal rate, S dot. The actual Kalman filter algorithm is summarized by the three matrix equations on the lower right. The matrix P is the covariance matrix that summarizes the state estimate statistics. The standard deviations and the correlation coefficients are contained within the covariance matrix. We propagate the state vector between measurements using the transition matrix. At the instant of the measurements, we compute the Kalman gain. We also update the covariance matrix after the measurement to account for new information that is supplied by the measurements. The complete set of matrix math for the new algorithm is totally defined by the underlying math model and its noise statistics. We have summarized the complete Kalman filter algorithm here. We have also simplified the Kalman gain math and the covariance update math based upon the single measurements and the form of the measurement matrix that includes only ones and zeros. We also show the state update expressions that use the transition matrix between measurements and the Kalman gain at each new measurement. Looking at the state update math between each measurement and then at the next measurement, we see that the calculations are very simple. For the linear system, the Kalman gains K can be pre-computed and stored. Also, the state update computations can be performed incrementally as the measurements are taken. For the FFT, all measurements must be available at the end of a symbol time in order to begin the FFT algorithm processing. The covariance propagation math results in a complete statistical performance prediction given a particular set of model parameters. This covariance propagation is independent of the measurement processing, which is very useful in the system design stage. We will use this in the continuation to provide the sigma A and sigma B in order to relate the estimation accuracy back to the communications data rate. Recall that we developed an equation to relate the A and B estimation accuracy to the number of bits per symbol time. As a final note, we show the residual process. This is the predicted measurement minus the actual measurement. We also show the predicted residual covariance. By monitoring the residual process as measurements are processed relative to its standard deviation, we can throw out bad data and we can detect when the assumed model has changed, as in the case of the presence of a discontinuity from a multipath delayed signal component. But wait, the Kalman filter is providing a covariance matrix for a state vector which contains the signal S and the signal rate S dot, not the estimates for the A and B modulation factors. We need to estimate statistics for the A and B and not S and S dot. We show here the expression for the state vector in terms of the desired quantities A and B. We can solve for the A and B with a 2x2 matrix inverse as shown here. This allows a transformation of the covariance matrix so that we can compute the statistics for the estimates of A and B. Given these statistics and the assumption that the estimates of A and B are uncorrelated, we can relate the estimation accuracy back to the number of bits per symbol as we showed before. Another quick but important aside. To allow a normalization of the carrier frequency, by revisiting the harmonic motion second-order differential equation and replacing the time variable with the carrier phase, we can normalize the solution so that the analysis results will apply to any carrier frequency. For a multi-carrier system model, we must select one frequency for this normalization, and the remaining subcarrier frequencies will be represented as a fraction of this frequency. Thus, for example, for a 2.4 gigahertz carrier with 64 subcarriers spread over 20 megahertz, the delta frequency fraction will be 0.00013. Another aside, the Kalman filter allows for arbitrary digital sampling intervals. This will include subsampling a carrier at a rate well below the carrier frequency. This graphic shows a 10 Hz carrier that is sampled at a rate 5.2 times below the carrier. You can clearly see a reduced frequency repetitive digital waveform within the sampled data pattern. We have added the continuous waveform that fits these subsampled data points. The frequency of this subsampled waveform is formed from three parameters: the original carrier frequency, which was 10 Hertz, the whole value of the subsample period, which is 5, and the added fraction to the whole value, which is 0.2. You see the expression of the equation down in the highlighted area on this slide. There's a great deal of information on subsampling a carrier coming from the SDR world. This simple rule that I have shown here seems to be a general relationship for the subsampled data, but we haven't found other locations where this simple model is provided. With a traditional heterodyne radio, there's a lot of hardware involved in the down conversion of the information encoded under the carrier. Also, noise and other corruption is contributed by the nonlinear heterodyne process, where two waves are multiplied together. Direct RF digital subsampling to arrive at a sampled reduced frequency perfectly preserves the amplitude and phase information stored within the modulated carrier and inserts no nonlinear operations. However, can subsampling be accomplished in a practical radio mechanization? Direct sampling the carrier is the goal for all software-defined radio, or SDR. So we are not alone in this goal to direct sample the RF. But is it really achievable? Can we subsample a 2.4 gigahertz carrier at 10.2 times or higher the carrier frequency? There's a good bit of literature on subsampling, but we haven't seen implementations of the type that we are proposing. The good news is that our methods are applicable even if the radio uses heterodyning to an intermediate frequency. But we will continue here under the assumption that subsampling is indeed practical. We look forward to hearing from you on this matter. This is an example of a 2.4 gigahertz signal sampled at 10.1 times below the carrier frequency. The blue background on the top curve is the dense 2.4 gigahertz signal. You cannot actually see the shape of the waveform. The black dots are the noisy samples. We're using a 64 QAM modulation, and on the bottom graph we show the A and B modulation values that achieve the waveform shown on the top. The symbol time is the period where the A and B values are held constant. Our sampling was selected somewhat arbitrarily as 20 samples per symbol time. Any acceptable demodulation algorithm must be able to decode the A and B values at the receiver with acceptable uncertainty so as to achieve an acceptable bit error rate. And thus we must use the 20 samples for the incremental processing. The new algorithm will be able to treat such arbitrary sampling patterns and to predict the statistics of the A and B estimates, and in turn will select a preferred QAM constellation, and then the number of bits per symbol become available. We must say something about the noise measures that we will be using here. The noise that we will add is added to the summed sample subcarriers as evidenced by our measurement model. So if all subcarriers had A and B values of 1, the signal power will be on the order of n, the number of subcarriers. We're adding up all the subcarriers with amplitudes of 1. The statistical signal power would take into consideration the probability of occurrence of the A and B values, which certainly is much less than 1. So our simplistic treatment of the signal power is a weak link in our discussions, but we will remedy this as we move forward with our work. Similarly, we are aware of the peak to average power ratio issues with OFDM. We will say more about this further along in this presentation. Without further discussion, let's jump to some digital results. Let's consider a single carrier with QAM modulation. The Kalman filter algorithm covariance propagation is used for these statistical results. Because the system dynamics and measurements are linear with AWGN, these covariance predictions are guaranteed to be correct for the selected model parameters. This chart shows the A and B estimation accuracy for 4 values of measurement noise standard deviation. The initial uncertainty in A and B is assumed to be 1.0, and this is used to initialize the covariance matrix at the start of the digital processing. This tells the Kalman filter that the A and B values are almost completely unknown. The estimation process reduces these sigma values as the sampling occurs. The time axis is shown in carrier cycles so that the frequency has been normalized to 1. The digital sampling is 10.1 carrier cycles per measurement. So at the 200 carrier cycle point, we have collected and processed about 10 samples. It can be seen that the sigma A and sigma B values are nearly identical as the measurements are processed. Recall that we earlier made this assumption that this would be the case. We will show a few characteristics of this simple single carrier estimation process on the next few slides. We have noted before that sampling at an even number of carrier cycles results in a singularity condition. This chart illustrates that concept. Notably, even a slight displacement of the sample rate from the even carrier cycle will result in good performance. We expect that the communication frequencies are sufficiently well known at the receiver so that we can stay clear of this sampling singularity. The chart illustrates the single carrier estimation behavior as we vary the sampling rate. We show subsampling periods from 20.1 to 100.1 times below the carrier. We see that the estimation results are not significantly impacted by the sample rate. This can be explained by the dynamic system model we are using for the single carrier waveform. Recall that the differential equation for simple harmonic motion had no additive noise. This means that the future state can be perfectly predicted from any prior state. In effect, this sampling of a predicted signal is similar to sampling a constant value repeatedly with Gaussian noise added for each successive measurement. This leads to a 1 over the square root of the number of samples reduction in the estimate standard deviation. This 1 over square root time history is shown on the small inset chart so that you can see the similarity of this trend. So what is the limit to the sample rate? Sampling at the lowest rate seems the right way to go. However, this assumes the carrier dynamics are perfectly predictable across the complete sampling time window. Consider, for example, a 100.1 cycle sample rate and 100 total samples. That's over 10,000 carrier cycles of prediction. Is the carrier predictor predictable over this time window? Some degree of carrier clock drift may contribute to non-coherence in the carrier over longer periods of sampling. The system dynamic model, based upon simple harmonic motion, can be readily tweaked to represent this non-coherence of the carriers. We will show this mathematically in a future presentation if there is interest in this subject. We have shown that we can predict the sigma A and sigma B for our communication system designs. And we have shown an example for the single carrier. We derived earlier an equation for the number of bits per symbol given the sigma A and sigma B. We can use this relationship to compute the data rate for a specific system design. On the right side of this chart, we show the sigma A and sigma B versus the number of samples. This is taken from a prior chart. On the right side of this graph, we have added the number of bits per symbol for the sigma A. The bits per symbol must be exactly 2, 4, or 6 in order to have a fixed BER design. We show two specific designs with the red circles, one at 4 bits per symbol, or 16 QAM, and a second at 6 bits per symbol, or 64 QAM. The bottom axis locations matching the red circles gives us the carrier cycles per symbol time that match the red circles. This information lets us compute the digital data rate in bits per second, disregarding the FEC and guard time to treat multipath. The equation computes the data rate. This equation computes the data rate, the bits per symbol time, the carrier cycles per symbol time, and the carrier cycles per second all go into this computation. We show the computed data rate for the two designs. We see that the 16 QAM design has 4 times the data rate of the 64 QAM design. This is a result of the much faster symbol time, 90 carrier cycles, than for the 64 QAM design, 550 carrier cycles. This interesting trend suggests that reducing the symbol time will typically outperform higher QAM constellations. We are now positioned to address the multi-carrier extension of the single carrier system design. And we will see that this is a very straightforward process with no loss of model fidelity. Because each of the subcarrier models are defined independently from the other subcarriers, the transition matrix will be seen to have a special form with 2x2 submatrices along the diagonal. These 2x2 matrices on the diagonal are identical to the transition matrix for a single carrier, but with a different frequency. For a 64 subcarrier system, the covariance matrix will be 128 by 128 elements. This is a symmetric matrix which offers some numerical simplicity, but the covariance propagation between measurements for this large a transition matrix becomes numerically difficult. Fortunately, this matrix math can be greatly simplified because of the transition matrix diagonal form. We show the simplified solution here as n times n minus 1 divided by 2 multiplications of 2x2 matrix products. Similarly, the measured matrix easily expresses the sum of the individual subcarriers as a row matrix with alternating ones and zeros. Simplifications of the matrix math using these model-specific matrix forms makes the Kalman filter tractable even for large numbers of subcarriers. The linear system dynamics and measurements with AWGN make the covariance propagation of the complete set of A and B values correct, as was the case for the single carrier model. The covariance matrix will provide a detailed time history of the A and B estimate convergence over time as the measurements are processed. In order to illustrate the multi-carrier demodulation, we will first show results for a two-carrier system. We know that increasing the subcarrier separation beyond a certain point will lead to performance that is twice the performance of a single carrier. That is, as the separation is increased between the carriers, the two carriers do not interfere and they behave as two independent communication system designs, as in the FDM communication system. In the past, as we have moved away from FDM towards more closely spaced carriers, we imply a requirement for orthogonality as a means of presenting interference between the carriers. But in fact, orthogonality of two waveforms is not a factor in the analysis that we present here. This chart shows a set of A and B estimate signals with varying frequency separation between the two subcarriers. The carrier frequency here is normalized to 1 as before. So we must model the frequency separation as a fraction of 1. We show performance for frequency separation values for a carrier of 2.4 gigahertz that range from 24 kilohertz all the way up to 1200 kilohertz. Recall that for 802.11a, the frequency separation for the 64 carriers is 312.5 kilohertz, and for 802.11ax with 256 subcarriers, the separation is 78.125 kilohertz. So our range of frequency separation is within the realm of understanding for 802.11. Now curves D and E are the farthest apart and are clearly representative of a separated carrier FDM design. The remaining curves have smaller separation, but can achieve the same estimation results with a larger number of samples. The point to be made here is that subcarrier separation, that is, successful demodulation of each subcarrier without interference from a neighbor subcarrier, is not related to the subcarrier orthogonality. Indeed, we can separate any two frequencies regardless of the spacing, so long as the sampling time is sufficiently long. This chart is a continuation of the last chart. It shows the bits per symbol for the prior two-channel system. The equation for the number of bits in terms of the A and B estimation accuracy is shown here and was derived earlier. Consider the two system designs. Number 1 has 256 QAM, or 8 bits per symbol, and design 2, 16 QAM, has 4 bits per symbol. These are shown at the red circles. We show the data rate for system 1 by multiplying 8 bits per symbol times 2 for the two carriers, and then times the carrier frequency, 2400 megahertz, and finally we divide by the symbol time in carrier cycles, 4,000 cycles. This leads to a data rate of 9.6 megabit per second. Again, neglecting the FEC and guard time for multipath. Design number 2, on the other hand, uses 1/5 of the bandwidth because of the much closer spacing of the carriers. And the data rate is only reduced by a factor of 2 to achieve a 16 QAM modulation. So we can achieve 5 times more bandwidth efficiency with only a data rate reduction of a factor of 2. The message here, as with a single carrier system, is that communication system optimization can be readily performed using the covariance matrix for the demodulated A and B parameters. That is, we can look at a family of multi-carrier designs, all with a fixed BER, and ask which system has the highest data rate for a specified system bandwidth. Leaping to a 64 subcarrier communication system is a simple parameter change in the covariance propagation model. This chart shows that leap. with a set of system designs for a varying number of subcarriers. The noise and frequency separation and sampling strategy is held constant for each of these models, so the only variation is in the number of subcarriers. The single carrier and two carrier models are shown at the top left for reference to the prior charts. Note that for the two carrier case, the A and B estimation accuracy for both subcarriers is reduced at the same pace, as only a single curve is visible for the 4 sigma time histories. That is, we have two subcarriers and A and B values for both subcarriers. They all lay on a single line. The 3 subcarrier models shows a different pattern. The estimation accuracy for the added subcarrier from 2 to 3 reduces at a slower rate. For the 4 subcarrier model, we again see what appears to be the two curves with the added 2 carriers accuracy reducing at the same rate. So these solutions seem to behave in a certain way with pairs of subcarriers. This phenomenon continues as new subcarriers are added in pairs, with the first 2 of the lower frequency converging much faster than the higher frequency carriers. The 64 carrier case is of most interest because of its relationship to 802.11. From 10 carriers to 64 carriers shown on the bottom row of graphs, the estimate sigma time histories all converge to a point on the time or cycles axis. This convergence point is exactly 1 over the normalized frequency separation, or 7,692 carrier cycles. Well, this is exactly the symbol time that would be expected from an implementation using the FFT approach. Aha! Have we just proven the optimality of the FFT solution? But wait. Recall the standard OFDM mechanization of the transmitter and receiver. For all OFDM designs, there were in fact 2 time history measurements, one for each of the IQ mixer outputs, as we show on this slide, top right. For 802.11a with 64 subcarriers, the IFFT is initiated with 64 AB pairs from the Quam constellation. The time history output of the IFFT is the real and imaginary results from the IFFT, or 2 separate time histories. We show here the mathematical relationship between the IFFT output and the A and B parameters that we have been investigating. So to compare with OFDM, the Kalman filter must be modified to handle the 2 time history measurements instead of the 1 real measurement. We will not go into the details of how this is done, but the Kalman filter is readily configured for this 2 measurement model. When this is done, we have the following results. On the left side, we repeat the design with no IQ mixer and a real output from the IFFT. How would you get a real output from the IFFT? You must populate 2 times 64 frequency bins with a second higher frequency half filled with zeros. So the result is 128 time history data points. So the receiver would take 128 measurements at a sample rate of 2 times the bandwidth of the transmitted signal. Aha! This is Nyquist at play. Recall before I questioned how we sample a signal at 20 megahertz to recover an encoded 20 megahertz bandwidth signal. The secret is that we use 2 measurements rather than a single real measurement. The right-hand pane shows the results of the 2 measurement Kalman filter. The convergent time is exactly 1/2 the convergence time for the case of the real data transmission. This was the goal that we originally established when we began this presentation. A few conclusions. We have shown that the OFDM symbol time can be reduced by a factor of 2 when we replace the FFT with an optimal estimator. We will provide a data rate improvement of a factor of 2 if we disregard the requirements for the guard time. This data rate increase was the primary goal for this presentation of the new approach. In summary, we have replaced the FFT processing in the receiver in order to remove symbol time constraints that were imposed by the FFT. We also have enabled both an arbitrary frequency plan layout for the subcarriers and arbitrary digital sampling plan, both of which were constrained by the selection of the FFT. Subsampling of the carrier is offered from the new approach as a means of implementing an SDR radio. Key outstanding issues that must be addressed are numerical implementation of the new method and practicality of RF subsampling. We have also discussed multi-carrier mechanizations that use only a real output from the transmitter rather than the real and imaginary time histories as with OFDM. For such a real information signal, can we use OFDM's IQ mixer for a second completely independent information signal, which would in fact be another way of achieving a 2x data rate? The proposed data rate improvement alone is sufficient to warrant further investigation of this method. However, there are more areas where OFDM can benefit from modern estimation. Channel modeling is a key motivation for OFDM, as frequency-dependent channel corruption may be present that influence A and B estimation. By sending the known A and B values in the preamble of the frame, we can infer the errors in these A and B values for each subcarrier, and we can make corrections during the data portion of each frame. Similarly, within frame correction can be made using the inserted pilot signals. Receiver frequency synchronization can be accomplished as a byproduct of the A and B estimation. The frequency uncertainty can be added as an additional error state that applies to all subcarriers. This will create a nonlinear model that can be treated using the extended Kalman filter form. OFDM's guard time must be added even when we do not expect multipath. A better approach is to adaptively detect the presence of multipath during symbol processing and adaptively extend the symbol time based upon the detected multipath. This model identification capability is well understood with modern estimation applications and can be used for this adaptive guard time purpose. The peak to average power ratio is an issue for OFDM. An MPSK, or phase shift key only solution, may be a useful method for managing the PAPR. That is, all subcarriers will have the same amplitude. Lastly, we have noticed some interesting variation in the estimation convergence for the lower subcarriers. That is, the carriers do not all converge at the same rate. This suggests that there may be a better non-equally frequency spacing that can offer even further symbol time reduction, at least for some subcarriers. We want to take a look at using pairs of closely spaced frequencies, with each pair separated from its neighbor by a larger frequency. We have interest in partnering to continue this work. There may be fundamental technical flaws in the presented material that would prevent practical implementations of the new methods. If such flaws are noted to us in the responses to this material, then we will correct these and resubmit the body of work. More importantly, We would like to continue this work with emphasis on practical implementations. Our preference is a near-term demonstration of the estimation approach to show the increased digital data rate using an actual transmitter-receiver pair. We're not looking for funding, but more a developmental partnership. We have submitted a provisional patent that covers most of this material. We will be flexible regarding the intellectual property as we discuss the details of a partnership. Please feel free to contact me at any time. Email is likely the best with a follow-up phone conversation.